So I met Hubert when he first came to Yale. We didn't really start collaborating until. Yes, I can hear an echo of myself.
We don't. Sorry, maybe it's my
Someone should
microphone.
turn off a microphone.
It's my microphone. Sorry, I'll turn it off.
Thank you. Yeah, there's the 2-second delay. That's better. So we didn't start collaborating until about 2000, and then we collaborated on about 10 or 11 papers, in fact. These were mostly on loop models and polymers and percolation. And I used to go to Paris, spent some weeks in Paris each year for quite a number of years. And that was a really good time. And Hubert was a very gracious host, and it was a good time. So thanks, Hubert, and happy birthday again. The echo seems to have subsided. So now I will share my screen. Well, first I'm going to launch that. And now I'm going to, I can find out how to share this. Seems to be an unfamiliar Zoom setup. How do I share the screen?
I think if you go to the option, perhaps you will see somewhere some dots, like 3 dots, and then if you go there, sometimes you have more options.
Yeah. Right here, share screen. Do you see it now?
Yes, yes, perfect.
Okay.
Thank you.
All right, good. All right, so I'm going to talk about something rather different from conformal field theory and so on. I'm going to talk about spin glass theory. And so I'm going to go over some of the concepts and rigorous results for short-range spin glasses. This is a little outline. I'm going to talk about Newman-Stein's metastate concept, and I'm going to talk about complexity near the end. Okay, so Ising spin glasses, really the basic definition goes back to Edwards and Anderson. It's written here, and we have nearest neighbor interactions, and Ising spins, and Jij are independent random variables. I can still hear an echo of myself. This notation down here, you can't see that, never mind.
We can see your pointer, yes. Yeah.
Okay, so can you see that? Yes. So this notation means an expectation value over J. Here I've done it for nearest neighbors. We can make it longer range, and I'll define that a bit. And the basic result of Edwards and Anderson was that there's a transition in a mean field sense. And in a given ordered state, the expectation of the spin average is 0, but the average of the square of the spin is not 0. So the spins order, but in some random way, and so they call this a spin glass. Then Schoenstein and Kirkpatrick proposed an exactly soluble infinite range model. And that led to Paris's mean field solution, which has quite a complex structure, as is well known. And many aspects of that solution have been proved rigorously by now to be correct. On the other hand, for the Edwards-Anderson model, a lot of questions remain unresolved. The Parisi school expects similar behavior as in the SK model, but other people, Bray, Moore, and Fisher and Hughes, proposed a simpler, seemingly simpler solution called the scaly droplet picture, which is still capable of producing complex behavior and glassy dynamics and interesting stuff. So this controversy of which of these pictures, or maybe something else, occurs in short-range spin glasses in, say, 3 dimensions is an unresolved question. And I'm hoping to shed a little work on this, little light on this.
Hi, sorry to interrupt. It looks, some people are telling us that they hear lots of echo. So it might be that some of the people online...
Yes, well, I can hear echo too.
Yes, it could be that some of the people online...
Everyone needs to mute their microphone, please.
Yeah, I was going to say...
It's due to Jesper.
Ah.
It's due to Jesper Jacobsen.
Ah, okay. Thanks, Jean-Michel.
It may be echoing back through my own computer too, I don't know.
It's due to Jesper microphone, I think.
Yeah, please mute it. We'll all be happier. Is it better? Done? Okay, I'm going to continue. So a feature of the Parisi solution or RSB picture is there are many ordered states or pure states, sometimes referred to as free energy values, and they're also arranged hierarchically or ultrametrically, although I'm not going to get into that in this talk. On the other hand, in the scaling droplet picture, it's assumed either implicitly or explicitly, but it's assumed that in zero magnetic field, there's just one pure state or ordered state and it's spin flip, just like again an Ising ferromagnet. So this is one of the central points and differences between what these different scenarios predict. However, the notion of a pure state is a rather subtle one because it only makes sense in an infinite size system. In a finite system, the Gibbs distribution takes a well-known form using the Hamiltonian written here, and this is defining this pH of S to be this expression for the probability. Beta, of course, is inverse temperature. So these are the well-known formulas, but they don't really make much sense in an infinite system because the Hamiltonian then becomes an infinite sum and it just doesn't converge. So it doesn't make sense there. So now we can come to the definitions that make sense for infinite size. These are called DLR states or Gibbs states. DLR stands for Dobrushin, Lanford, and Ruel. And not so complicated. So it's defined by saying that if we take the gamma is going to be the state, the probability distribution on spins. If we look at the spins in a region lambda, finite region, and we take the conditional probability on the spins outside, that's given by this Gibbsian formula as a function of the spins inside lambda, with the spins outside appearing as a boundary condition in effect. And the Hamiltonian includes the interactions between spins inside and also the interaction of spins inside with spins outside. So with spins outside fixed, these are the only relevant terms in the Hamiltonian, and then we can use the ordinary Gibbs formula. And this H prime is finite with probability 1, can be shown that it's finite if the sum of expectations of the magnitudes of the bonds leaving a given site I are finite. And that's independent of I because I always assume translation invariance. This condition defines what I call the short range case. Okay. So in general, I'm allowing longer range interactions and not only nearest neighbor. So this does not determine the behavior of the state at infinity, and there could be many different Gibbs states under this definition for the same Hamiltonian H. Then it's also true that convex combinations or mixtures of Gibbs states, weighted combinations where the weights add up to 1, are again Gibbs states. And we can then define pure states to be extremal Gibbs states, that is, Gibbs states that cannot be expressed as a convex combination, which in general would have to be an integral of other Gibbs states. And then a further result is that any Gibbs state has a unique decomposition as a convex combination of pure states. So here's an example of a convex combination. It involves weights W alpha, which are non-negative and add up to 1. And here I've written it as a sum, but in fact, in some cases, it may be that we would have to write this as an integral instead of a sum, an integral with some measure. And in this convex combination, the gamma alphas are pure states, the extremal states. So this is the real rigorous definition of a Gibbs state in infinite size, which makes no reference to finite size systems, except in a way in this definition here. Okay, so if we want a state in infinite size, why don't we just take a limit of a system, of a sequence of finite size systems, such as finite size systems with free boundary conditions? Well, the problem is that, at least in the low temperature region, the limit, L goes to infinity limit, may not exist. Or the limit of correlation functions, if you like. That limit just may not exist for fixed J's. So we fix an infinite set of all the J's all at once, and we use just some of them in finite size, but as we increase the system size, more and more of the J's and additional spins come into play until we reach the lattice Z to the D. So the fact that the limit may not exist is the phenomenon of chaotic size dependence. As we increase the size, the state may change to a different state and never settle down so that its correlation functions all approach some definite limit. And Newman and Stein connected this with the existence of many pure states. So they proposed the concept of a metastate. So by the way, Newman and NS stands for Newman and Stein. It does not stand for Neveu-Schwarz in this talk. They proposed this idea of a metastate, and in fact, a related construction was given earlier by Ising and Wehr in 1990. So there were two constructions of metastates. So a state is a probability distribution for the spins for fixed Jij's. A metastate is a probability distribution on infinite size Gibbs states for fixed Jij's. And basically, the way that one can construct this in the Ising and Wehr form is we first look at the joint probability distribution of bonds and of states in finite size, and we take a limit, and we can take a limit in the sense of convergence in distribution. I won't get into what that means. But we can get the limit, and we may have to use a subsequence of sizes. So the underlying idea is that if we use the joint distribution of spins and bonds, this may be better behaved than if we fixed all the bonds and then just looked at a limit of the state. So we take this joint distribution in the limit, and then we condition on the J's on the J's afterwards. That gives us the metastate. And that may just sound like I haven't done anything except take the limit, but it is different. First of all, this metastate exists. It's well defined, and it can be a non-trivial probability distribution on Gibbs states gamma. And in particular, the states that we get after taking these limits are actually Gibbs states. They still obey the definition, the DLR definition. So this shows that in fact Gibbs states in the infinite size spin glass do exist, which otherwise is not known. So this is the Ising and Wehr description. The Newman-Stein metastate replaces some averaging over bonds with an average over different finite sizes, but let's not worry about that. The Ising and Wehr is often the most convenient one to work with. Okay, so another way to think of this Ising and Wehr metastate is we can start with finite size system of size L, a hypercube of size L. We'll define some smaller hypercubes that are nested. We can look at the probability distribution for the finite size Gibbs state and take the marginal, just the restriction of the probability distribution to the spins inside lambda W, a whole system. We can get a probability distribution on those states because that changes as the disorder in the outer region between lambda L minus lambda R. As that disorder changes, we get different states, which we can see in principle in the innermost region, lambda W. So that's some probability distribution on these states. And then we take limits that keep the sequence of the inequalities of the sizes consistent, L to infinity first, then R to infinity, then W to infinity. And the result of that is the Eisenman-Weyr metastate. The words ground state there is a typo, actually. That shouldn't be there. So what the Eisenman-Weyr metastate tells us about is it tells us in the limit, taking limits of large systems, tells us how the ground state observed in a finite region, sorry, the Gibbs state, that should say again, how the state observed in a finite region in the window, lambda W, depends on the bonds, even on all the bonds in the outer region, even though they're now infinitely far away. So it's like dependence on disorder at infinity. The Newman-Stein metastate is similar. Sometimes they can be shown to be the same. And so this metastate may be trivial or it may be non-trivial. So just as Gibbs states may be trivial or non-trivial, they may consist of one or just two symmetry-related pure states, or they may consist of many pure states. The metastate can also be either trivial, supported on a single Gibbs state as a delta function, or it could be non-trivial. There are many different Gibbs states, which would be produced if we change the disorder very far away. Okay. So now in the scaling droplet picture, just to give examples, the metastate is assumed to be trivial and unique. And the unique Gibbs state contains only a single pair of pure states, or one pure state for non-zero magnetic field. And in contrast, in replica symmetry breaking, the Gibbs state is non-trivial, and the metastate must, in fact, be non-trivial as well. And this is responsible for some of the features of the Parisi solution. One could have other possibilities where the Gibbs state is non-trivial and the metastate is trivial, and vice versa, but I won't be talking about those in this talk. So I'm just going to define some things which I'll use to mention something quantitative about these metastates. So angle brackets mean the thermal average in the Gibbs state gamma. Square brackets with kappa j is the expectation over the metastate at fixed j. So that's really part of the disorder, but infinitely far away. And square brackets with the subscript nu is the expectation over the distribution of j, which could be Gaussian. And you see, when we take the limits, we can, all of the j's are still in play as part of the disorder, even though something at infinity got lumped into the metastate. And then a useful thing to define is this state rho j of S, which is the metastate average of a Gibbs state gamma of S. So that's called the metastate average state. And that's in fact a Gibbs state as well. And so an average in the metastate average state is given by averaging, thermal averaging gamma, and then an average over the metastate, the distribution of gammas. And so we have a dictionary that we can use to relate these to finite size calculations. In finite size, we have a unique thermal average. The kappa j average is the average over the disorder in the outer region, and the nu of j average is the average over the inner region. But then we have to take some limits. So now the following correlation function should reveal whether or not we have a non-trivial Eisenman-Weyr metastate. What we do is we take thermal average of SI/Sj in the metastate average state, we square it, as is typical in spin glass theory, and then we take the average over the disorder nu of j. So that's the limit of this kind of average here, where we do the thermal and outer average before we square, and then we take the average over the disorder in the inner region, and then we take the limits. And this differs from the usual spin glass correlation function. So this thermal average squared should go to a constant in large distances. If the metastate is trivial, then this C is actually the same as that, so it goes to a non-zero constant in the low temperature phase. But for a non-trivial metastate, the average over the disorder in the outer region can make this correlation function decay, even at zero temperature, and it can decay to possibly a smaller value, non-zero, or to zero, even at zero temperature, if the metastate is non-trivial. Okay. And what we may expect if it does decay is a power law decay. So that's my proposal, that it may decay as a power law. And so then we can define this exponent. Well, d minus zeta is the decay exponent, and we can define zeta in this way. And this can be thought of as related to some sort of fractal clusters that are flipped, that the difference between, at least for ground states, between different ground states. And so in this kind of picture, we would expect that there would be an exponentially large number of distinct pure states that we can see in a window of size W. And that may go as exponential of some power of W. And I argued in my 2014 paper that zeta prime equals zeta. That's really a conjecture. There's no very solid argument for that. Certainly no rigorous argument. And one may also expect that zeta prime, strictly speaking, zeta prime rather than zeta, should be greater than or equal to 1 in the Edwards-Anderson model. And I'm going to return to that point later, I hope. So if zeta is less than d, or zeta prime is less than d, then the total number of pure states in the metastate average state, well, it grows exponentially as a power of W. And this strongly suggests that the total number in the metastate average state, as W goes to infinity, is an uncountable number. So it's uncountable, but it's subextensive in the sense that zeta prime is less than d, or bigger than 0. Zeta prime bigger than 0 means subextensive. And now this would be in the metastate average state. In the replica symmetry breaking picture, the number of pure states contributing to a single gamma drawn from the metastate, in replica symmetry breaking, that's actually a countable number of pure states and not uncountable. So this is to do with the metastate average state itself. Now for the Eisenman-Wehr metastate, we can use the replica approach and the replica symmetry breaking field theory to actually calculate the correlator by using the Ising, because we just have to do the disorder averages in certain ways. And the result is that in high dimensions, this correlation function falls as 1 over distance to the d minus 4 asymptotically. So zeta equals 4, and this should be valid for d bigger than 6, where the loop corrections to the field theory calculation can be neglected. They're infrared finite. So that's a definite prediction which comes from replica symmetry breaking. And it wasn't a very difficult calculation for me because I referred back to results of De Dominicis and co. in 1998. For d less than 6, it becomes very difficult to calculate these correlation functions, and we're not very sure what is really happening there within the field theory approach. But we may expect that zeta decreases and reaches d so that the correlation function becomes a constant just at the lower critical dimension below which there's no transition at non-zero temperature. And this lower critical dimension is thought to be about 2.5 in spin glasses. And so we can also calculate other properties of the metastate and the overlap distribution using the field theory as well. So I'm just going to I won't go through this whole slide or the next one, but I'll just briefly mention that there are numerical calculations, which this one was in 3 dimensions and produces a non-zero number that's not equal to d for zeta, and some others, also some other evidence there. Some other calculations which I got into myself recently and extended, which however involve dynamics, and here one can actually check a whole function for different values corresponding to dimension of space in a long-range one-dimensional model. This gives very good agreement with the theoretical formula in the region where the exponents at criticality would be the mean field values. All right, so let me now go on to my second topic, which is closely related, and this is the notion of complexity. So Palmer suggested the name complexity for the entropy of the set of weights in the pure state decomposition of a Gibbs state gamma. So we take the same definition that I wrote before, And then we formed the Shannon entropy, if you like, or Boltzmann entropy. And he's also suggested that this quantity might be extensive, might be proportional to volume for some states gamma. However, this idea is a bit problematic because pure states are really only defined in infinite size, and so it doesn't make much sense to say that it's proportional to volume when the volume is infinite. So this is a rather awkward. Didn't seem to be a real solution to this, but a couple of years ago, my student Judith Hurler and I, in a paper on some other topics really, proposed a different definition, a better, much more robust definition. And the idea is to use the idea of mutual information from information theory and take the mutual information between the spin configuration viewed as a random variable, spin configuration in a window lambda, and the pure state alpha. And so then we can use the standard definition of mutual information, which you can look up on Wikipedia if you like. And this is this expression. It's got a log in it, so because it's an entropy type of thing. And this is what I would say is the complexity of this state. Or at least it's the complexity relativized to a window. So relative to the particular window, we get some number which will be finite. It's guaranteed to be finite. And as lambda goes to infinity, it increases. Perhaps it goes to a constant, or perhaps it goes to infinity. Then we can also study how it increases with lambda, which will be useful information if we could calculate it. And this mutual information, the meaning of mutual information as applied to this particular case is it's the amount of information that we gain about which pure state our configuration belongs to if we just make an observation of the random variable, which is the spin configuration in the window. So that's a limited amount of information, but as lambda gets larger, this gives us more information. So that's a key concept to try to absorb. And this replaces Palmer's definition as an entropy, and it reduces to that definition in some cases. But this is a good, robust definition. And in fact, it works for continuous spins and other things quite generally. So in the metastate construction, we can think of the Gibbs state as a random variable because it has distribution kappa. We can take the expectation of the kappa. That gives us a mutual information which is conditioned on G, and the expression becomes this, rather obviously. And this is all for given J's. So this I call K sub gamma. So this is the complexity of a typical or average Gibbs state drawn from the metastate. And we can also define the complexity of the metastate itself to be simply the mutual information between the spins in lambda and the Gibbs state G. So how much information we get about the Gibbs state, which Gibbs state it is, from observing the spin configuration. We can also define, since the metastate average state rho is a Gibbs state, we can also define its complexity like this. And these three quantities are related by this very simple relation, but the last one is the sum of the other two. Okay. So then I was able to find bounds on these. In the paper with Judith, we've used a very simple bound. If we have Ising spins and nearest neighbor interactions, then the point is the information about which pure state you're in, or any of the other ones for that matter as well, must be transmitted through the spins on the boundary of the window. And so it's upper bounded by the surface area of the window times log 2. This is basically from counting the possible boundary conditions. So this gives the simple W is the D minus 2 that some people expected, but it's limited to the case of Ising spins and nearest neighbor interactions. It can be extended easily to other discrete spins. It can also be when you get log of the number of states instead of log 2, and one can extend it to interactions to a finite number of other spins. You get a similar result up to a constant. But if you want to have arbitrary interactions that obey my short range condition that I had earlier, or to have more general spins, including for example, unit vector spins, then I recently obtained a different bound, and this works, while the other one works for all temperatures, including zero, this only works for non-zero temperature, and it involves the sum of the variances. And this sum, in some cases at least, does converge. And if you have short-range interactions of suitable types, then this again gives the surface something proportional to surface area, even though now each spin in principle interacts with every other spin. Nonetheless, the sum can converge and give the surface area. For longer range interactions, like power law interactions, there are other interesting forms that arise, but which I won't get into here. And so this does indeed give the bound that zeta prime has to be greater than or equal to 1 for the short range case, and some other expression for the long range cases with the power laws. So that's maybe not a lot of results, but at least it's some step, and the definitions of complexity here are very robust. So finally, the conclusion then. So the metastate is kind of an extra layer of structure in spin glass theory of probability distribution on Gibbs states, and it's derived from what happens in finite size. So although it's a distribution on infinite size states, it tells us something about what would happen in a finite size system. And this can be translated into measurable correlation functions, measurable in, say, numerical simulations anyway. And there's a quantitative prediction for, at least for high dimensions, for the value of the exponent. So it's a useful way to assess whether there are many pure states. And more quantitatively, the number of pure states can be defined more precisely as this complexity given by mutual information, and the growth, the exponent with which this grows with the size of a window, can be bounded. So finally, in the general picture is that it's widely believed that replica symmetry breaking is correct in the Edwards-Anderson model, at least in dimensions bigger than 6. D less than 6 is a bit more of an open question. None of this is proved rigorously anyway. And so what's still needed in the field is a proof of non-triviality or non-triviality for either the Gibbs states or the metastate in really in any dimension, in particular low dimensions. And so this is a hard, very hard problem. There are some results in 1 dimension, also some partial results in 2 dimensions, showing the showing that in some cases the ground state metastate is trivial. The metastate will always be trivial in the high temperature region, and whenever there's no transition at non-zero temperature, we would expect that it's trivial at 0 temperature as well, but that's not been proved either. So with that, I will conclude and wish Hubert a happy birthday once again. Thank you.
Thank you. I don't know if you heard us clapping because we now are in silent.
I hope you can still hear me.
Yeah, we do. So I pass you Hubert.
Hello, Nick. Good to see you. Oh no, it's gone.
Yeah.
I hope it didn't cut out too much while I was talking.
Right. Well, great. Thank you. I like this view of you. It's really very dignified. What is it behind you? Karnak? Or?
Yeah, that would be a good idea.
Yeah. So, just one question. You mentioned this complexity is not proportional to the volume. So how does it fluctuate? Is any guess about this?
Hello?
Hello, Nick. Do you hear us now?
Yes.
Ah, good.
Hi, Hubert.
So I was asking a question about the complexity.
Yes.
You said it's not proportional to the volume. That's correct? So
It cannot be.
do you know how it
Yes,
fluctuates?
cannot be. I don't have any information about the fluctuations in the complexity. My most recent bounds are only on the expected value of the complexity. The other one does not require an expectation value, but I have no information on how much it fluctuates.
Okay.
So that's completely open.
In 1D, is it something you can study?
Well, it might be. In 1D, long-range models would be interesting, but it's hard to do these calculations. And even in 1D, there were some things we can prove in 1D, but they're rather limited. And the cases that don't have a transition at non-zero temperature would probably have a trivial metastate.
Yeah.
And basically trivial complexity.
Okay. Okay, well, thank you, Nick.
Sure, thanks.
Thanks. Anyone else? Any question? Yeah, just a sec.
Could you say more about what can be proved in 1D?
Well, in 1D, I think I removed a slide about. In 1D, we can use a model. I mean, nearest neighbor is really not very interesting. So in 1D, we can use a model where the variance of Jij is a power law of the distance. So that defines sigma, okay? And then, okay, well, for sigma, for sigma in this range, there's a transition at non-zero temperature. And what I was able to prove is that at zero temperature, the ground state metastate, which is the zero temperature version, is trivial for sigma bigger than 3/2. But there's no transition at non-zero temperature for sigma bigger than 1. I made a mistake here. That should be not on the slide, but for the range where there's a transition is sigma between 1/2 and 1. And the metastate can be proved to be trivial for sigma bigger than 3/2. So even there's kind of a gap between sigma is 1 and sigma is 3/2, where I would expect that the metastate is trivial, but we don't have a proof for that. And we don't have any proof of trivial or non-trivial for sigma less than 1. At non-zero temperature for sigma bigger than 1, the metastate is definitely trivial just because it's the high temperature phase.
Thank you very much.
Thanks.
Nice to hear Adam's voice there. Hi, Adam.
I think that's all for questions. So thanks again, Nick. And
Okay.
sorry for the technical problems
Okay.
at the beginning. Bye.
Thank you very much.